Okay, everybody, let's get started. Today, first we have Samuel. Samuel is going to be going over analysis and defense of automotive networks. I'm going to hand over control to him and he's going to get started.
All right, so thanks for waking up early with me, guys. My name is Sam Hollifield. This is analysis and defense of automotive networks. And that's my team. Just below my name, I work with a talented group of individuals, and we work with the Cyber and Applied Data Analytics Division at the Oak Ridge National Lab, and I can even show you my face. Perfect. So we're at the inside the National Security Sciences Directorate at ORNL, and our primary project has been to try and develop some sort of vehicle agnostic way to defend automotive networks. And so my goal today is to tell you a little bit about the work we're doing at ORNL, maybe give you some breadcrumbs to be able to do some automotive analysis on your own, and get you excited about hacking on cars, because it's something that's really blown up the last few years. It's something you can do on the cheap, and it's quite a bit of fun. So I say that also with the preface of I've never bricked my car. It would probably be a whole lot less fun if I permanently damaged it. So to tell you a little bit first about the Oak Ridge National Lab. So we started on the backbone of the Manhattan Project. So back in like the 1940s, there was a need for some plutonium to become enriched and build a big old bomb because we were in a serious war. So Oak Ridge was chosen as the site for the very first national lab, or well, it wasn't at that time, but we ended up being the first and also being the largest. There are about 17 national labs in the nation, and I'm a little bit biased, but I think we're the best. So of course, you know the story, the war ended, and then we still had all these facilities that were used to produce like nuclear materials and radioisotopes and a bunch of really nasty stuff. So instead of going more toward like weapons grade research, we went more toward the open community of science research, in that we now had all these facilities to be able to develop some really cool medical isotopes so we could treat some cool cancers. And then the lab kind of exploded, and I like to say if you can get a PhD in a field, then you can research it here. So anything from like advanced material design to biological studies, chemical, and of course my group, we work in cybersecurity. I'm in the cybersecurity research group. And one of the main things that's interesting about working at a lab is that we're not really industry and we're not really academia. So I know a lot of folks are in industry, you know how that works. You're building tools either for customers or profit or for some reason. Academia, whereas, is more on like the highly theoretical side of things, where you're the guardians of knowledge, teach it, discover it, preserve it, pass it on. And national labs really exist to find problems that the nation's currently having and figure out a way to solve those. So we take a lot of problems from the very theoretical side and fundamental side to actually applying them and using them in some real world situations. Of course, one of those things is vehicle security. So we actually have a laboratory dedicated just for vehicle security, and it's out at the National Transportation Research Center in our Hardin Valley campus. So we can put a car on a rolling dynamometer, have it in motion in a safe environment, and perform more or less like cyber evaluations to see if we can develop and tool and create some defenses for vehicles. So this is one I like to show, is so our cars really, truly hackable. Are they vulnerable? This was a video of a gentleman we had. Oh, there we go. This was the video of a gentleman we had coming from the Air Force, and he was a fighter pilot, so he was actually our first guinea pig. We figure if he can fly jets really, really fast and shoot at things, we could probably put him in a car and hack it, and he'll be okay. This is just an Arduino board with a CAN bus addition that plugs into the OBD port of the car, and he's going to accelerate to about 10 miles per hour. The Arduino is going to recognize the speed of the vehicle, and then it's going to trigger an attack. And all this attack's doing is it's just sending like junk into the port. And you see some like really scary flashes. You don't get audio through GoToMeeting, but the engine revs like way up, and then all the relays start clicking. And this is like a dumb attack. Like you plug in, and we have like a random number generator that just sends a random payload across messages. So what really allows us to do this kind of like scary infiltrating of the vehicle? Well, it's a network inside of the car that's called a controller area network. And I'll call it a CAN or a CAN bus interchangeably throughout the talk. But in a sense, there are a variety of networks that actually exist on your car, from everything that handles multimedia to like your interior inside your like door panel will have its own little kind of network. But the one that is really critical is the CAN. And the reason for that is kind of twofold. One is that this is the network that primarily connects all of the critical electronic control units or ECUs in your car and allows them to talk to each other. The other problem is that it's actually mandated. So any vehicle produced after 2008 has to have this thing called a CAN bus. And the reason for that's largely like emissions purposes for most of it. And that's because, you know, prior to 2008, OEMs would kind of have whatever proprietary network that they wanted to have in their car. And so it became kind of cumbersome to do testing when you had to have, you know, 15 different devices to speak the right language to be able to interact with the car. So the CAN was mandated in 2008, and it's got to be on every vehicle. And in terms of electronic control units or ECUs, your vehicle can have upwards of, 100 or more of these on a brand new luxury vehicle. So everything from like engine control module, transmission control module, like seat belt safety status control module. You can essentially take a noun and then stick control module after it, and your car will almost certainly have it. So that we have a ton of ECUs in your car, and they're connected to a network, but the kicker is this network has some inherent vulnerabilities. So one's it's an open broadcast bus network, meaning anywhere you plug in on this network, like the OBD port, you can see all of the messages that are being sent from everywhere else that's on that same CAN. There's also no way to really verify that who's sending the message is who they say they are. Like the attack on the previous slide, we were using an Arduino to spoof a bunch of messages, randomly. We didn't even know what we were sending, and the car seemed to accept it as if it were absolute truth. And it's super easy to actually identify a CAN bus and connect to it. So for one, it's located in your OBD port, the On-Board Diagnostics port on your vehicle, which is like right usually next to your steering wheel. You may have had a mechanic hook into it, or if you're in a state that does emissions testing, they may use that as well. More specifically, it's actually located on these two pins. So pick pin 6 and 14 on the OBD port, if you're looking at the little chart here. And this is where it's mandated to be on every car after 2008. So not only does a vehicle have to have CAN, it actually has to exist on these two pins as well, because back to the reason of you don't want to have 15 different tools to accomplish one task. So at a glance, you can say, well, I know where it's at, I can connect to it, and I can play around. I will say this, that maybe since 2018, 2019, automakers have been getting kind of hip to the fact that people are plugging into their OBD ports and messing around with their cars. And so a lot of OEMs have started putting like a filter or a gateway on the other side of that OBD port where you don't get all the raw data from the ECUs. You can only request the specific things for like emissions testing or diagnostic purposes. You don't get that kind of unadulterated access. That's okay though, because I said CAN exists on two wires. And I just wanted to show this little slide to kind of illustrate that you have two wires on CAN. One's called a CAN high and a CAN low. And the reason for that is they're a differential signaling bus. So CAN high will kind of move up in voltage and CAN low will move down. And that's how you transmit your ones and zeros. And because the vehicle is really inherently noisy, like from an electromagnetic standpoint, these guys are twisted together to try and do a little bit of shielding to avoid any sort of integrity loss from the messages. So kind of simply, even if you have a car where the OEM has disabled some of the access at the OBD port, you can maybe pull apart your dash or under your hood or inside of your wheel well and find a pair of twisted wires. And typically the only pair of twisted wires you're going to see on a car are from this CAN bus. So as an example of that, we had a big bus we were doing a little bit of evaluation on. And this guy was actually filtered pretty heavily at the OBD port, so we couldn't plug in and get, you know, raw data. We were only getting what the manufacturer wanted us to see. However, this bus had a really nifty service port where you could just unlock and open up this big bay and then have access to all of the ECUs. So these are all ECUs inside of the right side of the picture. And then all we had to do was take a pair of piercing alligator clips, find the twisted wires, clip into them, and then we're getting every message on the network that we're not supposed to see, or they don't want us to see. They don't want to see not supposed to. So that's kind of the physical side of your CAN bus. Now, if you're interested in maybe interpreting data or looking at some of the logical stuff inside of CAN, this is actually a CAN frame. So this is more or less what you're going to see once you plug into your car and everything's running. You're going to get a whole bunch of data that probably goes super fast. And there's a lot that goes on inside of a CAN frame, but there are really two really important fields that exist. One's the arbitration field, or the arbitration ID, or AID. I might interchange that. I'll try to spit it all the way out so I don't acronym soup everyone. So the arbitration ID exists to kind of give the message a name or an ID and allows us to index and prioritize that message. So in a sense, an arbitration ID kind of determines the priority of who gets to speak on the bus. And a simple way to kind of think about that is the lower the arbitration ID, the more precedence they have to actually talk inside of the vehicle. So a really simple dumb attack like the one I showed you earlier, that could be accomplished by just spamming ID 000 at a rate that every other ECU, or faster than a rate that every other ECU talks at. And because it's 000 is the lowest arbitration ID you can have, no other message will be able to actually propagate throughout the bus. Now, the other important field is your data field. And this is kind of as you would expect, your payload or your actual, your message contents. And the data field is super small. So it's one of the real kind of handicaps of CAN. Is it can only transmit up to 64 bits of data. So that makes it really hard to add any sort of like encryption schemes or ways to further obfuscate the data outside of just filtering, firewalling, and not providing access. There are some more technical things that go on inside of here as well, but we're not going to dive into that just for the purpose of this. I want you guys to be familiar with the arbitration ID and the data field. So now you kind of know what a message may look like. We use a lot of tools on our day-to-day when it comes to like reading CAN from the data, like software tools. And the most useful and versatile, I would say, is a Linux tool called CANutils. So you can, in Debian do like apt-get install CANutils. And it's a tool that was actually made by Volkswagen and was released to be open source. And it works with a lot of things. So it works particularly with any Linux-based system. So say, Raspberry Pis, BeagleBones, your own laptop, so on and so forth. You can install CANutils and use it to translate, send, receive data from your vehicle. And this is just a screenshot of one of the tools inside of CANutils called a CAN dump. And this just like dumbly dumps all the messages as they come in on message receive, print message, more or less. So on the left-hand side, you've got the timestamp. CAN 0 just denotes the interface, so CAN like WLAN 0. And then the actual message or frame is over on the right. So you have the arbitration ID, and then it's separated by the #, and then 64 bits or 8 bytes of data in hex. So there are some nuances to CAN, right? Like you can't just expect everything to work the first time. And I was told when I started on this project, there's a steep learning curve, and then after that, it gets really easy. So some of the nuances are that each vehicle's CAN will have a preset bit rate for all the messages or for all the ECUs to talk to each other properly. Most modern cars, it's 500K, but it can vary. And that's important because if you get inspired after this talk and want to hack on your own car, you can actually plug in with the wrong bit rate and cause some pretty scary errors to pop up and interrupt communication between all the ECUs. Another thing is it's actually meant to be terminated with a 120 ohm resistor as well. So practically, a lot of times, if you're just messing around in your garage, that doesn't quite matter. But it's occasionally happened to me that I plugged everything in, it's all working right. I can't figure out why I'm not getting any messages, and it's because this car is very finicky and it requires actual termination to work. I'd also mentioned earlier that you can have upwards of, say, 100 ECUs in your car. But you can also have like 200 or 250 arbitration IDs on your car. So as a result, that simply means that each ECU may broadcast more than one arbitration ID. In fact, one ECU may broadcast the bulk of the arbitration IDs in your car, meaning that many different messages types can come from one ECU. Another important distinction about CAN is that each vehicle from like year, make, model, trim will likely have unique encodings for their CAN messages, meaning that you know, my 2015 Volt will not be entirely the same as a 2016 Volt. The reason for that is partly just simply different devices, and as vehicles get upgraded, new you know, messages are needed to support all the functions. But another reason for that is that automakers follow largely security through obscurity. So they don't really want to broadcast or really enumerate and tell you what the encodings of their messages are to avoid a lot of intense reverse engineering efforts. And, you know, of course, the big ones like performance tuning, you don't really want someone to break into your ECU, pull out your firmware and have fun with it. Another important thing to think of is that you actually may have more than one CAN on a vehicle. So although in your OBD port, those 2 pins are mandated and legislated and required to exist, like in my Volt, for instance, it's got like 4 CANs throughout it. So each one of those has its own separate stream of data, and some of them are more important than others. And of course, you can't just like take a USB cable, cut the ends, wire it up, and then expect everything to work when you have it plugged into your laptop. So you do have to have a little bit of specialized hardware in order to talk CAN. And at minimum, you need like a processing unit, like laptop, Raspberry Pi, you know, like single board computer that can support CAN. And then you need some of the hardware that actually talks CAN. So one of those is a CAN controller. So that actually sends to the processing unit the logical framed format that says this is an arbitration ID, this is a message, now I'm going to dump it to your terminal. The CAN transceiver passes the actual physical bits to the CAN controller so that it can pack those into the right message structure and send it to the processing unit. And vice versa, the processing unit will say, send this on CAN, the CAN controller will pack it into arbitration ID and message, then send to the CAN transceiver, which will turn it into physical voltages that will send over the 2 CAN wires, CAN high and CAN low. And I probably should have said this earlier, but it can be super dangerous to like just plug something up to your OBD port. I gave a version of this talk at CodeMash this year, and I didn't put enough disclaimers into the talk itself. So one of the attendees got really excited. We built little devices for this talk based on a teensy, and they were actually like going out to the parking lot and plugging into their car. And so one guy didn't cut all of the like wires, the extra wires that come from your OBD port, because we only need 2, but there's like 16 in there. And so when he plugged into his OBD port, his wires crossed and touched, and he had like really big sparks, and it was kind of scary. And I'm like, oh man, can I be held liable for this? So as a result, now I'm going to tell you all the way through the talk not to do anything I say, and don't plug stuff into your car. So now that we plugged into our car, so I want to demonstrate for you guys actually using the CAN util software to do a little bit of reverse engineering on your vehicle. And so I'm using this tool called ICSim, or it's Instrument Cluster Simulator. And it's written by Craig Smith. So if you're familiar with the Car Hacker's Handbook, this is a tool he actually created. And so what I'm doing here is I'm messing around without an actual car. So I'm bringing up what's called a VCAN. It's a virtual CAN interface. So it allows my computer to speak CAN without any sort of hardware required. And then I'm actually going to feed this, this virtual CAN interface to the instrument cluster simulator. And the instrument cluster simulator will transmit actual CAN messages through the virtual CAN as if it were a car. And it will allow us to practice some reverse engineering techniques before plugging into our own car, which we shouldn't do anyway, so that's okay. You can use like an Xbox controller or something and get really fancy with it. I was just using my keyboard. But there's a lot of functions inside of this tool that you can try to reverse engineer. And what I actually want to try to work on is we'll do the turn signal. So this tool I brought up is called CAN Sniffer. It's another one of the tools that's inside of the CAN Utils package. And this allows us to see which messages are changing. So there's a ton of messages inside of a CAN, and it can get really messy to try to look through them manually. This guy helps us out. So I'm gonna hit left turn signal and see if I can find a message that's changing based on the turn signal. I didn't, well, right turn. So I saw arbitration ID 188 there and kind of in the middle. It's flashing 02 when I hit the right turn signal. And I think 01 when I hit the left. So it leads me to believe this arbitration ID encodes the turn signal. I just want to double check that. So I'm going to use CAN Send, which is also one of the utilities inside of the CAN Utils package. And I'm going to send that one and see if I get a response. Okay, cool. So I'm getting some left turn signal. For all intents and purposes, right, like this is a cyber attack. Right? This is something that we probably shouldn't be able to do is simulate the turn signal. So I'm going to try 03, and then we get hazard lights, which isn't even an option or a feature inside of ICSIM. This was kind of a simple attack. It's an injection attack, and it's really messy. So what happens, and the reason that the turn signal doesn't like stay lit all the time, and I had to keep resending it, is because the actual legitimate car is saying, well, my turn signal's off, and it keeps repeating that message until you flip your turn signal switch and the legitimate ECU says, well, the turn signal's on. So we're always fighting with the fact that the turn signal's physically off, but it's still considered, I mean, for intents and purposes, an attack. So I'm gonna go ahead and accelerate my car up to 60. And what we're gonna see is if we can figure out where maybe my speed is located inside of these messages. And that's actually pretty hard. So while it's easier to identify these kind of binary messages like turn signal on, turn signal off, or hazard on, hazard off, or door open, door closed, locks on, locks off, it's kind of a scary one. It's far more difficult to identify some sort of like time series dynamically changing value. And you will spend a lot of time in your driveway messing with this just to figure out where your odometer may report the speed. So there are easier ways to go about analyzing some of the data inside your vehicle. One way to do that is through the On-Board Diagnostics service. So this is, like I mentioned earlier, you may have like a mechanic that will plug into your vehicle and do some analysis. And this is actually the kind of service they use in order to get ground truth or to get the actual happenings from your vehicle. So you can request a whole bunch of information from the car, and instead of trying to read some obfuscated CAN messages, you can enumerate and figure out exactly what it's doing. So if you're like a performance tuning guy, or like I had an older car that didn't really clearly enumerate like my actual miles per gallon over the lifetime, so I wanted to figure that out. I just use these services to do a little bit of math to figure out my fuel consumption versus my distance driven. Now the actual onboard diagnostic service, it fits on top of CAN. So if you're familiar with the OSI model, it's closer to like an application layer, whereas the actual CAN protocol is closer to our like network down to physical layer. So there are actually some other things that I'm not going to get into, but there are some other kind of additions to CAN that are built on top of it. And CAN is largely just a network, and you can do a lot of things with it, including retrieving diagnostics. So there's a really cool Wikipedia article here, and if you don't want to remember it, I know it's kind of hard to click from a PowerPoint. You can actually just Google like OBD2 PIDs, stands for parameter ID, and those are the enumerated values that we can actually request from a vehicle. And so the way that it works is you must figure out what sort of data you want to ask for, And then you just ask the car, and the car will immediately shoot back and say, well, here's the info. So because this is all standardized and it's used by emissions testing and mechanic shops, this all works on a standardized arbitration ID scheme. So you don't actually learn which raw arbitration ID is transmitting this data. So instead you learn what the data actually is and then maybe try to match that or find that elsewhere. And how it works is you send a request on arbitration ID 7DF, and then many other ECUs will reply to this broadcast for diagnostic queries. Most commonly, just as a tidbit, your engine, like main ECU, will live on 7E8, and that'll tell you a whole bunch of data. And then you just parse the data that's given back from the standardized message structure. And you can get a ton of data from this. This is just pulled from the Wikipedia article. Current data, you can get stored diagnostic codes, you can get some test results, you can request, reset your check engine light so you don't have to buy like a fancy tool or go to Advance or something and have them do it. And this is just a quick snapshot of kind of all the information that you can ask from your car. So there's over 150 possible parameter IDs. And there's no way that one car will support all of these for no other reason than a lot of these are specific for like electric cars or maybe not electric cars, maybe more like gas cars versus diesel cars. Like you can't have both types of fuel in one vehicle that I really know of. And so you can actually ask your car which messages it will reply to. That's one of the standardized parameter IDs that you can request that's available in that Wikipedia article. So you just send the request at the start and you say, hey, what will you reply to? It'll shoot back a whole bunch of hex and you just parse that as binary. I think a 1 means yes, I support it, and a 0 means no, I don't. And then you can build a list to request from your car based on that. So once we discovered that this kind of onboard diagnostic service exists, we realized that we were going to waste a lot of time trying to understand CAN data from the driveway when maybe we could leverage some of these diagnostic queries in order to automatically look at the encodings of messages. And that's really important because CAN inherently has like a tokenization and translation problem. So I mentioned earlier that all the networks are obfuscated, so you don't know what is being said by each message. Further than that, it's not really clear when you're getting bytes back where the actual functional message happens. So this one kind of makes sense. You have a CAN signal of engine RPM. This is an 8x8 grid layout of a 64-bit CAN message. So the bytes go all the way, from 7 to 0 there. The engine RPM takes up the first 2 bytes. So that kind of makes sense, right? Like takes up 2 bytes. Then in the next byte down, you have battery voltage, takes up the first 5 bits of the 3rd byte, and then the current gear is the last 3 bits. So there's not a clear separation when you're reading in hex where these different message encodings, or I'll call them signals now, where these different signals will be split and where that byte boundary exists. And further than that, so you can run into issues of like, is this also a sign number? Does it include negatives? And the most frustrating thing is that your endianness can actually switch mid-byte too. So you can go from reading 5 bits little endian, and then you have to switch your ordering and read the next 3 as big endian. And there's no real, cohesive way to be able to understand that. Or I should say there used to not be up until maybe a year or 2 ago. So we developed this pipeline. It's called Automotive CAN Tokenization and Translation. We call it ACT. And this tool allows us to leverage diagnostic queries in order to automatically extract these signals from a car without spending time in our driveway. And the way that it works is first we just learn maybe where those cut probabilities happen. So like going from the first 5 bits, we try to learn that the next 3 bits are a separate signal. Then we try to determine if that endianness problem does happen, where we have to start reading the bits in the opposite order. Once we do that, we can figure out if there might be some negative numbers that exist inside of here, whether they need to be signed or unsigned. And finally, and the really cool thing is we leverage the diagnostic services earlier to then find where those signals might exist, like practically in the CAN. And I have just another quick demo. So I'm using a Raspberry Pi here, and I'm going to plug her into the OBD port, and then we're going to go for a short drive, and I'm going to record some data. So the device is right there above my steering wheel, and the green light's flashing. That means it's trying to determine the speed of the CAN so that we don't break my car. Then the red light flashes with the green. That means we're requesting the VIN of the vehicle, and then we're trying to figure out which diagnostic queries it'll actually reply to. When I press the button and the blue light starts flashing, we're actually sending a ton of diagnostic requests to this vehicle. So I'm saying, like, what's your speed? What's your RPM? What's your mass airflow? Over and over and over at a really fast rate. And so I'm just going to go on a short drive. And this is actually my wife's car, because one thing I learned early on working at the lab is that you don't want to brick your own vehicle. Like, it's always best to brick the lab's vehicle, but can't go on campus right now because of the COVID situation. And my wife's car is a little bit older, so I told her I'd rather brick her vehicle. And then she got mad until she realized, like, oh, that means I'm making a new car. So I collected a bunch of diagnostic data here, and then we're actually going to be able to parse this. So on the back end that I didn't record, I ran the ACT pipeline because it takes a few minutes on the Raspberry Pi. They're not exactly like beefy processing units. But essentially, we've written a little tool that once we get the translated database file back from the vehicle, that lets us understand the signals that are encoded inside of CAN, we can actually visualize these now in real time. And so I've got a little screen. There it is. So I've got a little screen, and this guy's actually going to give us every arbitration ID that we see on the card, and then enumerate the extracted signals from ACT so that we can see this stuff in real time without requesting diagnostic data anymore. And so there's like timing advance in here. Then I think another one has vehicle speed, engine coolant temperature, RPM, and of course, when I select RPM, we get 0 because the Volt's an electric hybrid car. It runs on battery most of the time. But one thing I figured out was if you pull your hood latch, actually, then it will force the combustion engine to kick on, and then we get the spike up to about 1600 RPMs. And that's just one signal. We can also view like coolant temperature and see like what it is right now. Among every other, the 150 possible parameter IDs that can be extracted from arbitration IDs in this car. And then there are also some unknown signals. And what the unknown ones mean are that we weren't able to find these messages inside of the known diagnostic queries, but we were able to identify that they're a unique signal that's encoded within the message. So we can still graph these as well and understand them. And there's a big motivation for understanding this data. So for one, we're using this for intrusion detection systems because we want to extract signals, turn them into a time series, and tell when they're no longer continuous. Another thing may be aftermarket understanding. So as mentioned earlier, if you're a car person and you want to figure out your fuel economy or your like 0 to 60 time, but you don't want to send stuff to your vehicle while it's driving, well, you can use this kind of tool in order to read dynamically from the bus so that you're not requesting diagnostic queries. And then, of course, there's a big market for performance tuning where it may be valuable to understand which arbitration ID and ECU are sending, say, the throttle percentage, and then figuring out an easy way to identify that and then manipulate it so that more power is going to the car. So we're using it for intrusion detection. So I got to talk a little bit about that from a security standpoint. Because CAN's limited in the amount of bits it can transmit, it's very small. It's hard to develop, like I said, some sort of encryption scheme. So we're looking at more of a vehicle agnostic way to create an intrusion detection system. And most IDS research so far has fallen into 3 categories where it's either physical, so you're looking at primarily the voltage or the physical layer, and that kind of has some drawbacks because each car can be really finicky, and further, it's a really noisy environment from an electromagnetic standpoint. So we don't really look too much at physical so far at the lab. We've looked at frequency and timing based, and this one really only uses like message headers and the frequency that each message is sent. And then the next kind of field of research is the data field inspection. So that's where we're actually looking at the contents of each message and trying to determine if it's an anomalous or an attack. And there are two ways to look at this. One is like payload, saying are kind of treating each field as just a binary blob. And then the next is our signal-based idea, where we extract a time series of data from the car. And most research done so far in this field has been either frequency or payload based, but our ACT tool has really allowed us to do some signal based research that a lot of people haven't been exposed to. An idea of the timing based detection of automotive cyber attacks is here. And the idea is that each CAN message is sent at a regular interval. And so when you do a dumb injection attack, like you're trying to turn the turn signal on or off, that should be able to be detected because now you've added extra messages into this arbitration ID. So we really simply just look at a snapshot of time, get some data, and then if the timing of the message is off by a certain percentage or a threshold, then we alert and say that an attack has happened. So this one requires very little overhead. It's really easy to put on a Raspberry Pi and work. But the downfall is that, let's say there's like a poison the well attack and messages are being sent at the correct interval, but they're not being like correct messages. So we also look at payload base. So the idea of a payload base is that we break each message into like bits, so either zeros or ones, and we try to determine the probability that the next message will have a 0 or a 1. And so here's a little illustration of the predicted data and then an attack that had been sent to the vehicle. And you see that like some of the bits I colored in red aren't the predicted value. And we essentially just generate some sort of threshold saying if n number of bits are outside of the threshold, then an attack has happened. But it's still kind of difficult to determine at a glance like whether or not there's been an attack, which leads us to our signal-based results. So the idea here is that we can use our ACT pipeline to extract a whole bunch of signals from this vehicle. And even if we can't translate them, but we can identify that they're signals, we try to learn what maybe the next value will be. So here's an example of like an engine RPM attack where we're trying to spoof the engine RPM. You see this one at a glance is a lot more obvious. Like on data point 8, it drops down to 0 and then back up to like 2600, which really clearly demonstrates that there's been an attack launched on this car. And so that leads us to believe that our signal-based approach will be more effective, but we're still in kind of the mid stages of this, and we need to do a lot more testing to really verify that hypothesis. So here's a quick demo of one of our detection schemes. So this is a really simple timing-based detector that will just count the number of messages. And an important thing to think of is we need to detect an attack on the car before the car physically reacts. Once the car reacts, there's an attack. So the device up on the top is actually the IDS, that's a Raspberry Pi, and then the Raspberry Pi down on the bottom, underneath the speedometer is our attack device. It's got a button on it, but when I press the button, it's gonna launch an attack to the car, one of those dumb injection attacks, and I want to catch it before the car physically reacts. So we're gonna launch the attack, and then I want to see a red light on this IDS. Oh, perfect, red light just before the car reacts. So there's not a whole lot of time. I mean, the attack's launched and the car reacts immediately. The engine revs up, it wants us to stop safely now. We lose all power on the gas pedal. We need to be able to detect that quickly. And there's a lot of research going into this now. So some of the recent work on this has really exploded since, say, 2016. But if you're interested in getting into this field, it's brand new. It's quite exciting to be working on some like cutting edge sort of research, because this is a field that's projected to grow and continue to grow, and with the ultimate goal of making our vehicles more secure. Chances are, honestly, you probably won't get hacked yourself. But for someone who may manage a large fleet of vehicles, or like rental cars particularly, like rental car companies hate when they rent to me, because I mess with all those new cars. All right, so we're about to wind down now, and I just want to recap, make sure we're all on the same page. So we learned a little bit about CAN today, how to send and receive some messages, how we can use message timing to prototype a really basic but effective IDS, how the diagnostic service can be used to generate some ground truth from our vehicles. And like to reiterate that you should not do as I say or as I do, and don't plug anything into your car at my division. So if you guys are interested in this research and want to do some more reading, I'd recommend starting with the Car Hacker's Handbook. It's fantastic. It has a lot of good resources and a lot of good details on like CAN utils and using diagnostic services. If you want to get more technical into CAN, the KVASR education on CAN bus is completely free, and it goes more into like the protocol layer and the nuts and bolts of what a CAN message is and how a CAN network operates. If you want to spend a little bit of money to learn about it, I really recommend the Automotive Electrics and Automotive Electronics. This is like a textbook, so it costs a little bit of money, but the information contained therein is, I mean, invaluable. It goes very in depth. And of course, it's not a good conference talk without a shameless plug. So if you want to learn about some of the math that we use to create our ACT pipeline, then that's available on Archive. And you can, like, I think just search ACT and Archive and ORNL, and it should pop up fine. So if you want to get started with some hands-on tools, I use the KVASR CAN to USB tools. I use one called the KVASR Leaf Lite V2. It's a couple $100, but you can plug it up to your laptop, or you can run a VM, and it works fine with Linux, and it's fantastic. If you want to go the cheap route, you notice, I mean, throughout my talk that we use a lot of Raspberry Pis to do this stuff at the lab. And pretty much any consumer level single board computer now can run CAN with some really cheap add-ons. If you need some more processing power, like for some of the like more in-depth machine learning-esque stuff we do to try and understand like time series detection, the Raspberry Pi can't quite run that. So we have to use something like an NVIDIA Jetson TX2. That guy's a couple of $100, but it has onboard CAN and it works great for processing some models. And of course, if you want to break the bank and go the professional route, you can get something like Vehicle Spy, which it's a tool that has a nice GUI and it supports a bunch of networks outside of CAN. So some of the other ones I mentioned at the beginning of the talk, you can also read with Vehicle Spy, but it's quite expensive. And then finally, I do have a special offer for you guys. So this might be a long shot. I gave this offer when I did the Code Mash presentation in January, and that was like a 4-hour talk where we built teensy devices and then walked people through the like coding the scripts and everything. But I love my Knoxvillians. So if you want to not spend time wasting in your driveway to understand some signals, and you have a car, you can generate your own data, meaning like, I do love my Knoxvillians, but I can't like help you get started from scratch on getting diagnostic queries from your car. If you can collect the data, augment it with diagnostic queries, then get into contact with me through email or Twitter or Discord or however you can, and we'll try to coordinate some of the analysis so we can run the ACT pipeline on your car and get you some signals back and maybe get us some good signals as well. But I appreciate you guys waking up early for this first talk today. And I hope you were able to learn a little bit about cars, and maybe you're a little bit more scared now to take a trip post-COVID. Thank you.
Okay, we do have a few questions for you. First, from Heather White, we have, does the National Transportation Research Center work with the Army NGCV Center in Detroit?
I'm pretty sure we have in the past. I'm not sure to what capacity we still do. I was actually lucky to be able to visit that facility last year, and we talked about doing some visits, but due to the situation right now, nothing's really panned out. But there's a lot that goes on at NTRC outside of vehicle security, so it's untelling, to be honest.
Okay, we also have Mike, who asked, I heard that at one point in time, the ODB port was only active when the car was in park. Was that true?
I'm not sure about that one. I've not seen a case where that's explicitly true just yet, but most of the cars that I've worked on are 2015 or newer. And the biggest thing I've seen there is that they'll work all the time, but a lot of them will only respond to the diagnostic queries. So you don't get any sort of like raw CAN data to be able to do analysis with.
Okay. David asked, have you looked at BMWs? How do their systems compare to other manufacturers? And I'm able to use tools to modify I am able to use tools to modify many settings in my 2016. Newer models have aftermarket software changes that are warranty supported.
So that is actually one brand that has been elusive for me. Is I have never plugged into a BMW, so I can't really answer that. But if you're around Knoxville, Kevin, after the COVID ends, then let me know, and I can give it a shot if you want me to.
Samuel wants to know if you can fudge a legit message, timed, e.g. a timed one you know is coming, by forcing bits high or low. Can you not bypass any IDS in a seemingly unfixable way?
So that is a good example of how the timing-based IDS has some flaws. Because the way the priority works on the CAN, I said the lower arbitration ID will win the priority to speak on the bus. That actually works all the way through the message. So if you have two messages queued up at the same time, a 0 will effectively overwrite a 1 and then stop that message from broadcasting. But that can also get kind of messy. And that's why some techniques such as being able to extract signals and figure out the discontinuity between it could be really effective in finding some attacks.
And lastly, we have Alex asking, have you tested any vehicles that can implement CAN message authentication protocols? What are your impressions?
So I'm not sure what really constitutes a CAN message like authentication protocol. We've seen a lot of vehicles that will have like counters or maybe some kind of bits appended at the end that are some kind of identifier. In a lot of cases, those work, but in some cases, the vehicle seems to respond in kind, even though there's not a correct counter or not a correct identifier.
All right, thank you, Samuel.